Well, by now you have conducted the molar volume of hydrogen gas lab and collected data for that and created a spreadsheet like this one. And you've either collected or gathered data from another group or from your entire class. And now we need to graph this data. The purpose of this lab, remember, is to determine, or really to try to recreate that 1 mole of a gas at standard temperature and pressure will take up 22.4 liters. Now, you in the lab did not use an entire, produce an entire mole of hydrogen gas, and as you can see from these numbers, you created very small moles, amounts of hydrogen gas. And so you also have small volumes. So we need to figure out how we can analyze this data. And the best way to determine our experimentally determined value is going to be to create a graph with this data and look at the slope of the graph whenever our line of best fit is the equation for that is in y equals mx plus b format. So that's the goal of this video, is to help you graph your data and do a little analysis. Now, before we actually graph the data, notice that I am in Google Sheets. And you should have your columns probably set up something like this. Each teacher might have required a little bit different what they want in your data table. But at the least, you have to have the moles of hydrogen gas and the adjusted volume of hydrogen gas in liters. That makes sense because we want to know how many liters are per mole of gas. So we need liters and moles here. Another thing to check before you graph your data is, are your numbers kind of close to each other? So notice here, like this number is 6.2 times 10 to the minus 4, 6.8 times 10 to the minus 4, 5.4 times 10 to the minus 4. If I had something in here that was 6.5 times 10 to the minus 3 or times 10 to the minus 5, I might want to relook at that number because I might have missed a 0 in my data entry, and that can have a significant impact on your graph. The same thing over here with your adjusted volume. Just do a quick check your milliliters. If you collected 10 milliliters, 10.0 would be correct with sig figs here, and then you adjusted that to liters, it would be 0.01 liters. But whenever we adjust that for not being at STP here in Colorado, for not being at standard pressure of 1 atmosphere, it should be a little bit less than that. So 0.0086 liters would be like 8.6 milliliters, and so that makes sense. That number makes sense. Same thing here, 11.2. That's a little, it's around 0.009 adjusted. That seems to make sense for liters. So point being, just check your data and make sure that it kind of makes sense. And it's really easy in all the calculations we did to make a minor mistake that can really impact the overall graph that comes out here. So to create this graph, we're going to need to select the columns that we want to actually graph. So like I said before, we're going to go ahead and highlight. So click on this cell and drag to highlight those. Now we also want to highlight another row, and so before you click on the next row here, which is going to be the D column, you're going to hold down the Control button. So I click Control, and then I click and drag this column as well. That's going to tell, if I call it Excel, I apologize, I'm used to Excel. That's going to tell Google Sheets that you want to graph these two data columns against each other. So we're going to come up here to Insert, Chart. And when you put this chart in, it's automatically Excel. Google Sheets thinks it's really smart, and it's going to pick what it thinks that we should do. And in fact, it's right this time because it picked a scatter plot. So you'll notice here, if Excel picks something different for you, just come over here and find the graph type that you actually want, which should be the scatter plot, which is what we have here. Now, you're going to notice that it's already done several things. One, it's put a title up here, which we're actually going to remove. It's also placed hydrogen gas in moles on the bottom here, and the volume of your hydrogen gas on the y-axis, and so that's what it should look like when we're done. Do a quick spot check all of your data points. If you have a good trend, they should be increasing and have like a positive correlation. If you got some weird numbers and it seems like one of your data points is way off the charts, you probably have an issue with data entry or calculations somewhere that you need to go back in and check. So now that we have this information, like I said, I prefer to get rid of a title because when we're doing scientific papers, we don't use titles on graphs and charts, we use captions. So I'm going to get rid of that. Your teacher may require something different of you and just follow their directions. Now what we need to do is see the trend for this data, and the trend line is going to show us the correlation between the moles of gas and the volume of gas. A couple of different ways to do this. The easiest way is to just click on one of these data points, and over here that's going to give some options. And if you can't get to it that way, come to Customize, all right, and you'll see all these options for the chart. Click on Series. So this is just another way to get there. And either way, either method you use to get there, you should see down here some options. And we want to click on Trendline. That's going to automatically add a line of regression onto our graph. Now, it's important that we know the two things about this line. One, we need to know the equation of the line. Remember, the slope of a line is rise over run. So in this case, our rise is liters, volume of our gas is liters of hydrogen gas. Our run is moles of hydrogen gas. So if you think about the slope of our line is actually rise over run, or liters per mole. If we have the slope value, that's going to give us our experimentally determined value for this lab, which is really what we're looking for, is how close is that number to the actual value of 22.4 liters per mole at STP. So come down here on the side to label. We need that equation, so we're going to click use equation under label. You're going to notice up here it has added that equation. So for this one it says 22.8 times x, or so 22.8x plus, and then there's this tiny little number here from being off the y-axis or the x-axis. This is in y equals mx plus b form. So our slope for this line is 22.8 liters per mole of hydrogen gas. So at this point, this is really the main stuff that you need for your chart. You do need to add a caption, which is should describe the trend line here. The other thing that doesn't seem appear that my graph is put on here, because I didn't check the box. We also need to know the R-squared value. So down here, you should, where you clicked use the equation, also you need to click on use the R-squared, show R-squared value. You'll see here R-squared equals 0.941. If this is all you need and you know how to interpret this data, then you can stop the video now, because I'm done with that part. I'm just going to talk a little bit about data interpretation here. Remember in class we talked about two key parts of data analysis. One is the accuracy of your data, and two is the precision of the data. Remember, accuracy is how close you are to the actual accepted value. In this case, the accepted value for a mole of hydrogen gas at STP is 22.4 liters. Our experimentally determined value for this data set is 22.8. Now, you're going to be asked in your lab write-up to calculate the percent error, and you'll find that percent error equation in your density lab from your course pack. And it's basically just the accepted value minus the experimental value divided by the accepted value times 100, and that'll give us our percent error for our experimental value. Now this is going to have this particular data set has a pretty low percentage of error. You may get higher percentage of error of 5 or 10 or even 15%, and that's okay. There were some places where we had error. If you have 20-30%, then you probably made some pretty big mistakes when you're actually completing the lab. And so that's one of the pieces of data we want to look for. The slope of the line is our experimentally determined value, and that's what we use to determine the accuracy of our data here. Now, precision is repeatability. You have multiple data points here. And what we want to look at is how close are all of those data points? How closely do they fit this trend line here? Then the program here gives us an R-squared value, which is basically tells us how well the trend fits with the data set. An R-squared value close to 0 means there's really no correlation. Those points are spread all over the place. An R-squared of 1 is a perfect following the line. It means every dot fits on this equation that is on the line. Now, this is a fairly precise data set. It has high precision because the R-squared value is close to 1. 0.94 is pretty close to 1. And that makes sense. Look at how closely the data points are to the actual line here. If the data points were a little farther off, we might see an R-squared of 0.7 or 0.8, but this is a very precise data set. And like we said, it's also a very accurate data set. If you get something like this, congrats, you did a really good job on the lab, and you have very low, not very much error in your procedure. That's it for now. Use this information to help you write up your lab, and if you have more questions, don't hesitate to ask.